This lesson is using graphs with linear functions, and the objectives are to use linear graphs to solve equations, draw graphs of linear functions, and write linear functions from graphs. Linear graphs are a useful tool for solving equations, providing visual representations or making predictions about data. There are multiple ways to graph linear equations. We will explore the following two techniques. The first is to generate a table of points, or ordered pairs, and plot them, and then connect them with a straight line. The second is to use the equation to identify the slope and the y-intercept, and to use these two pieces of information to generate enough points to connect and draw a linear graph. The skills and techniques used for evaluating and graphing linear functions can be extended to nonlinear functions with some modifications. Linear functions are the simplest example of algebraic functions and will develop the skills needed to move on to more advanced mathematics. Linear functions can be solved using their graphs to either solve for the output of a function for a given input value or to find which input values will produce a predetermined output. The difference simply comes down to which coordinate axis we should start from. In this first example, we're asked to evaluate f of x for a given input. So the graph on the right has no equation, but we have the graph. We can evaluate the function for f of x. And the question says, use the graph to evaluate f of 2. So this means that you must first locate x equal to 2. And the horizontal axis is the x-axis, so this is x equal to 2. We see that if we were to move down from here, we would not hit the graph at all. So instead, we want to move up from that location. If we move up, we will intersect the graph at this point, and we'll cross-reference it with the y-axis, and we see it produces a value of 1. This is also depicted in the image down below here. We see that from 2, if we move up to the graph, it intersects the graph at the location where y is equal to 1, so we can say that f of 2 is equal to 1. This was evaluated strictly from a graph, not knowing the equation, and producing the output. We can also solve for a given x from a predetermined output. Again, we're going to use the same graph. We don't have an equation for it, but instead the question is slightly different. It says to determine which x-coordinate does the function f of x equal negative 2. The first step is to restate this question. Since f of x equal to negative 2 is the same as saying y equal to negative 2, the question could be reworded to say, what is the x-coordinate when the y-coordinate is negative 2? This means we must first locate negative 2 on the y-axis, and then we would move horizontally, in this case to the right, until we touch the graph, and we would cross-reference that point with the x-axis, and we see that it is approximately at the location of x equal to 1/2, and that is depicted here in the image below. So when y is equal to negative 2, we would say x is equal to 1/2. Graphing functions is an important part of mathematical analysis. As we learn to draw graphs for different types of functions, linear and nonlinear, we are able to anticipate data trends just by becoming familiar with the shape of a graph and the direction in which it will advance. As previously mentioned, we will focus on two methods for drawing the graph of a linear function. So example 1, graph a linear function using a table of values. The technique of plotting points from a table of values can be used to graph any function, whether it is linear or nonlinear. This is beneficial because if you do not know the shape or the direction of a graph, you can ascertain such information by plotting more points. Consider the linear function f of x equals 2x minus 1. We know that it is a linear function because earlier we studied that linear functions have equations where the variable exponent is positive 1 and where the variables do not multiply one another, and where the variables are not in the denominator of a fraction or under a radical. So it satisfies all of that criteria. We know that its graph will be a line. Since f of x equals 2x minus 1 is a linear function, we know the graph is a straight path. Therefore, we really only need 2 points to graph the line. However, it is suggested that we graph more than 2 points because this will help us catch if we make a mistake on our part. If we generate a bunch of points and something is not in line with the other, it'll cause us to double check our work. So in this example, we're asked to create a table for 2x minus 1, and we need to choose some x values. The very popular choice is to use -2, -1, 0, 1, and 2. But depending on the coordinate plane you are provided, you might choose different x values. Here we see we can choose anything between -10 and +10, and we can choose by multiples of 2 or multiples of 5, whatever we feel comfortable with. But we'll use the standard -2 through +2. After we have our x values, we put them into the table, and we generate the y values for each x value. So this means that this first value here, -5, is the result of evaluating f of -2, because that is the x value. Since f of x is equal to 2x minus 1, f of -2 would be 2 times -2 minus 1. And we can see that f of -2, when we simplify and combine, is -5. And then we would do this for the next x value. F of -1 is equal to 2 times -1 minus 1. 2 times -1 is -2, and then subtract 1, and we get f of -1 equals -3, and that's the value we see here. And I'll leave the rest for you. You can plug in 0 into the function, you can plug in 1, and you can plug in 2, and you should verify that you get these corresponding y values. From here, we should see that each of these is an ordered pair. So the first ordered pair, remember ordered pairs are always xy, so that first ordered pair would be -2, -5, and we would plot that. -2 on the x, -5 on the y, and we put our first point. The next point would be -1, -3, and we plot that. Then 0, -1. Then we have 1, 1, and 2, 3. We can connect all of these points together, and that is our linear graph. Next, we can use the slope-intercept graphing technique. When a linear function is expressed in the form f of x equals mx plus b, it is referred to as slope-intercept form. This is because the m value is the slope of the linear equation, and the b value is the y-intercept. Therefore, if we have the equation g of x equals 1/2 x minus 4, we would say that the m, or the slope value, is 1/2, and the b, or the y-intercept, is -4. And to graph the line, we start with step 1, which is to plot the y-intercept. So you go to the y-axis, find -4, and put a point. And then step 2 is to use the slope to generate additional points. So recall that slope is equal to rise over run. And that means that we will rise +1. So we will go up 1, and we will run +2. We will go to the right 2. And from the y-intercept, we go up 1 over 2, and we put a point. And then we can repeat this, up 1 over 2, put a point, up 1 over 2. And all of these points we see are in line. And we've graphed our linear function. So m equals 1 over 2 means move 1 up and 2 right. Or if we didn't have room to move 1 up and 2 right, we can reverse that and say move 1 down and 2 left. And that's an OR statement. We have a choice based on where we have room to move in our graph. Again, if I start at my y-intercept of -4, I can move 1 down and 2 to the left. So 1 down and 2 to the left, and we see that still falls on the line. So we like to have both of these options on how to move between points using the slope, depending on what type of space we have on our coordinate plane. So we've generated a bunch of points. The more points we generate, the more precise our graph will be over longer distances that we're drawing it, and then we connect all of the points together with a line. So try this one on your own. Pause the video here, extract your slope and y-intercept, plot them, connect them with a line. Then unpause the video and see if your answer matches mine. So I see the slope is -2, and -2 can be written as -2/1, and this means to move 2 down and 1 to the right. Or if I don't have room to move 2 down and 1 to the right, I can say move 2 up and 1 to the left. So that's our slope. Then our y-intercept is 3. That's our b value. And we begin by plotting a point at the y-intercept of 3. And now I'm going to use move 2 down and 1 to the right. 1, 2 down, 1 to the right. Do that again. 1, 2 down, 1 to the right. Or if I go back to my y-intercept at 3, I can move 2 up and 1 to the left. And we see that all of these points fall in line. And that is a drawing of our linear equation. So just to take a moment to compare the graphs that we've just drawn, we have a graph for g of x equals 1/2 x minus 4, and we have a graph for f of x equals -2x plus 3. And we see that the g of x has a positive slope. Positive slopes move up and to the right, and positive slopes are classified as increasing. So we read our graphs from left to right, and we see that if I trace this graph from left to right, it's moving in an upward direction, and that is known as increasing. If we look at f of x, there is a negative slope. -2 is multiplying x. The line moves down from left to right, and negative slopes are classified as decreasing. So if I trace my graph from left to right, we see that it's moving in a downward trend. That is negative slope that does that, and we call that a decreasing graph. We also have special cases for linear equations. Those are horizontal and vertical lines. When the slopes of linear equations are either positive or negative values, we get slanted lines. Positive slants up from left to right, negative slants down from left to right. But what if the slope is neither positive nor negative? There are 2 special cases for this, where the slope is not positive or negative. These cases are zero slope and undefined slope. Zero slope means the line is not increasing or decreasing, it simply stays flat. When the slope is equal to 0, the line is a horizontal line. Consider the equation y equals 0x plus 2. We see the slope is 0, and 0 times anything is 0, and we can simplify this equation to be just y equals 2. Whenever an equation has the format of y equal to a number, that will give us a horizontal line. Another way to think about the equation y equals 2 is that it is the collection of all points that have a y coordinate that is 2. So there's a list down here, and if you look at all of the y coordinates, they are all 2. And you can pair that up with any x value you want. So if I plot this first point, -3, 2, It's here on the graph. Then the next point was negative 2, 2. And then negative 3 halves is negative 1.5. Then negative 1, 2. Then 0, 2. Then 1/2, 2. Then 1, 2. We see we can plot all these points, and when we connect them, we get this horizontal line. And if you choose any points on this line and put it into the slope formula, you get 0. So 0 slope is a horizontal line, and the equation is y equal to a number, and that number is where it will cross the y-axis. Undefined slope means that there is no number that can represent the slope. It is the result of a slope formula such that the denominator is equal to 0. 0 in the denominator is undefined because division by 0 is undefined. When we work with fractions, fractions are another way to express division. You cannot divide by 0 because that would unravel all of the laws and properties of our number system. For example, consider the mathematical statement 8 divided by 2 is equal to 4. Well, we can reverse this. We can say instead of 8 divided by 2 is equal to 4, we can say, well, what's 4 times 2? And it is equal to 8. When we reverse that, this is known as the inverse property between multiplication and division. However, as soon as you define division by 0, the inverse property will fail. How would you define 8 divided by 0? Well, if you said 8 divided by 0 was 0, then the inverse property says that you should be able to multiply 0 by 0 and get 8. And we see that that would be false. So we cannot define division by 0, because if we did, that means the inverse property would have to be a result of that, and everything would start to fall apart. So moving forward, anytime there is a 0 in the denominator, we say it is undefined. The graph of a line that has undefined slope is a vertical line. A vertical line consists of all points with the same x-coordinate. So if we consider the equation y equal to negative 1, it is the collection of points where we have many different y values, but all of the points have the same x value, which in this case is negative 1. If we look at this list, all of the x values are negative 1, and they're being paired up with different y values, just like we did with our previous example with the horizontal line. So let's plot some of these points. Negative 1, negative 3. Well, that's off the grid here. Negative 1, negative 2. We have that. Negative 1, negative 1/2 right here. Negative 1, 0. Negative 1, positive 1. And we see that they create a path that is vertical through negative 1. And if we were to choose any two of these points and put it into the slope formula, we would get some number in the numerator, but we would always get 0 in the denominator. And 0 in the denominator is undefined. Undefined slope is often called no slope. A common mistake that students sometimes make when considering a phrase like no slope is they think it's the same as 0 slope. They are not the same. No slope means that there is no number that can represent the slope. However, 0 is a number, so no slope is not the same as 0 slope. No slope is a vertical line. 0 slope is a horizontal line. So finally, we can classify horizontal lines as linear functions and vertical lines as linear relations. This is because the horizontal lines will pass the vertical line test with exactly one intersection point, but the vertical lines will fail the vertical line test. A vertical line has only one input value in its domain, but that one input value gets paired up with infinitely many y values. So if we were to draw a simple example here, and my horizontal line is in blue, and my vertical line, no matter where I put it, will only have one intersection. But if we look at our vertical line, If I draw a vertical line, it will have infinitely many intersection points with this blue line. So it fails the vertical line test. So next we want to write linear equations from their graphs. Given a graph of a line, we can write the linear function once we've extracted the slope and the y-intercept. We will use the slope-intercept formula, f of x equals mx plus b, again, where the letter m is slope and where the letter b is the y-intercept. And if we look at this graph, we can easily find the y-intercept. We say, well, it's crossing the y-axis at 1, so that is our b value. And if we have two distinct points on the graph, we can use that to calculate the slope, and we'll use the definition rise over run. So how far up do I have to go from point B to get to point C's height? And we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we say how far to the right? 1, 2, 3, 4, 5. So it's 9 over 5 is our rise over run. And we would plug 9/5 in where we see M. We would plug 1 in where we see B. And we would get f of x equals 9/5 x plus 1. And that would be the equation of our linear graph. Now, the other thing just to note is this graph is increasing from left to right. So we know the slope is positive. That's just a simple observation we make. This is a positive slope. We expect our result for the m value to be positive just because it's going up from left to right. So here's example 2. Pause the video here, work it out, see if you can write the equation. After you're done, unpause it and check your results with mine. So we start with the y-intercept. We see b is equal to 4. And I have another point I can locate here. From left to right, I see the graph is going down. This is negative slope. So I expect my m value to be negative. And I'll put the negative in front of the fraction. Now I have to count the rise. So how far up or down am I moving? And to get from this first point to the second one, I see 1, 2, 3, 4 down. And then how far to the right? 1, 2, 3. So the slope is negative 4/3. The y-intercept is 4. And we can plug this into the function mx plus b and say that f of x is negative 4/3 x plus 4. And that's how simple it is to write our equation from a graph when we have such clean points like this. That is the end of this lesson. So again, go back, watch the video as many times as you need, take notes from it, then move on to the practice section, check your work with the answer key. Once you feel prepared, go on and take the quiz.